So we have this joint research collaboration between NYU and KAIST, which I think is a great thing, and it's a university-wide effort. And one of the centers that we have is in the topic of AI, and Julia Stoyanovich at NYU and I are co-leading that center. And we just got started, so we don't really have any concrete action items, but this is the first thing that we are doing, that I am doing actually. Julia doesn't actually know about this. I'll let her know after this happens. But because language models are such an important topic right now, I think it's very timely and exciting to have this series of talks and a panel session today. And so Ha and James and Minjoon are all very young and very active members of the NLP community. And so I am so glad to have all of them join us today. And we're going to start with Ha's talk. Let me just start by saying Ha has been at NYU for a few years. She's done really great work in various topics within NLP. And rather than me just going on, I'll just let Ha begin her talk on in-context learning, right? So Ha, if you can just share your slides and begin.
Yeah, sure. Okay, can you see my screen?
Yeah.
The slides. Okay, cool. Yeah, so let's get started. And thanks a lot, Alice, for the nice introduction and for inviting me to this series. By the way, can you hear me clearly? Because I'm hearing some cutoffs. Okay, all right, cool. So I'll continue. All right. So the topic today is to share some of our recent work understanding in-context learning abilities of these large language models. And so recently we have seen a paradigm shift in natural language processing. And so previously, if we want to achieve high performance on tasks, we've spent a lot of time obtaining high quality annotation and developing task-specific models. But now that's replaced by just training transformers, a large amounts of raw data, and just using the next word prediction objective. And then we add massive amounts of compute and engineering efforts, we will get this general purpose models like GPT-3 that can be programmed in a sense to perform many different types of tasks. And what's amazing about this model is that even though this next word prediction is a very simple learning objective, there are surprising abilities coming out of these models once we scale them up. For example, they can learn from just a few examples through in-context learning. They can learn from explanations in the chain of thought prompting, and they can also learn from declarations by just following the instruction given by the user in the prompt. And these abilities emerge during the scaling process by just learning to predict the next word. So we were very excited about this capabilities, but at the same time, we're also very confused why they have this general abilities just from doing language modeling. So in this talk, I will try to share some of the recent work trying to understand this in-context learning ability in different contexts. So first, I will talk about recent work analyzing and evaluating how models do reasoning using chain of thought prompt. And if there's time, I'll also briefly talk about earlier work on training models to perform in-context learning better through meta-learning. Okay, so let's get started. A chain of thought is a prompting method that demonstrates how to solve a task. So in standard prompting, we give the model the input-output pairs in the prefix. And then in chain of thought, in addition to the input and output, we additionally give the model this natural language proof and show the model how the answer is derived. And this technique has shown to significantly improve performance many reasoning tasks, including the math word problems shown here. Okay, so the improvement is very surprising, but there are also lots of unanswered questions about the reasoning abilities of large language models. So for example, is the answer actually provable from the generated chain of thought? Because it's plausible, then maybe this chain of thought just helped the model to better retrieve similar math word questions from the pre-training data. So they're not really used to perform reasoning. The other possible explanation is that maybe the model has already trained this math word problems, because we know that OpenAI has been collecting data through this API and then, collecting human annotations on that and then fine-tune the model. And the other question is also whether the model is doing this reasoning systematically. What kind of mistakes do they make? And in order to answer these questions, we really need to inspect the generated chain of thought in addition to just measure the answer accuracy. So that's the main goal in this project. So our plan is that so if you just take this math word problems, because it's all in natural language, it's a little bit hard to analyze what is going on in the generated chain of thought. So our plan is to take the chain of thought, which is in natural language, and then convert that into logical forms that we can process and analyze automatically. And in addition, we also want to create fictional scenarios where the pre-training knowledge cannot be leveraged, because we would like to separate memorization from the general reasoning ability. So we want to give the model completely novel scenarios like this, synthesize the facts, and see if the model can reason with this in these fictional scenarios. Okay, so in this work led by the postdoc in our group, Abhir Saparov, we synthetically created this data set, which consists of a context. So this is basically a set of facts, such as each cat is a carnivore, every carnivore is not herbivorous. We have this collection of facts, and then we give the model a query, such as Faye is a cat, and then we ask the model to prove whether Faye is not herbivorous, whether this statement is true or false. And then in the answer consists of a chain of thought, so a proof as well as the label, which is just true or false. So typically, like in math word problems, you only evaluate the final answer, which is the number. So in this case, that's binary. But in this case, we really want to analyze the generated chain of thought. Okay, so the nice thing about this data set is that first off, it's parsable, because these are very templated. We can easily use a semantic parser to convert that into logical forms that we can analyze. And also it's programmable, meaning that we can fully control the data generation process, and we can vary different hyperparameters to control the degree of complexity of the generated examples. Okay, so remember that our goal here is to analyze the generated chain of thought. So specifically, we convert this natural language chain of thought into some formal proofs. Then we try to analyze each proof step in the chain of thought. So the first question we want to check is whether this is a valid step, meaning that it is provable from the previous steps. So this is kind of a measure of the local correctness. And so we have three possible types of steps. So the strictly valid step. So one thing I didn't mention is that in this data set, we only use a single deduction rule, which is modus ponens. Okay, so it could be strictly valid, which means that it's provable using only modus ponens. And it could also be broadly valid, meaning that it's provable using some additional deduction rules. Like cats are carnivores, carnivores are mammals, and then we can conclude cats are mammals. Or it could be invalid, so it just cannot be proved from previous steps. And then for each proof in the chain of thought, we also check what we call atomicity of the steps, so whether it is provable with exactly one application of a deduction rule. So because we observed that sometimes the model may skip steps. For example, it might say Faye is a cat and then directly say that Faye is carnivore without stating this premise that cats are carnivores. So this is what we call a non-atomic step. And finally, we also check the utility of the step, because oftentimes there are multiple things that you can prove, but not everything is related to the final goal we're trying to prove. So this is trying to check if the role of, so whether this the step is correct in a more global sense. So here is one example where the step is valid, but it is not that useful. So we call this a misleading step. So suppose we want to prove is not herbivorous. Then given the premise is carnivore, the shortest path is to just say carnivores are not herbivorous. But you could also prove that every carnivore is a mammal. This is a valid step, but it doesn't take us closer to the final conclusion we're trying to prove. So this would be a misleading step in this case. The other case is just, it's not misleading. So this would be a correct step. Okay, and we perform this proof analysis. So we generate a bunch of examples and we analyze these proofs using chain of thoughts generated by different models. So these are all different sizes of GPT-3 models. And then we use gradient decoding. We also control the number of hops and the ontology type in the generated examples. All right, so the first thing we try to look at is whether the label accuracy is correlated with the proof accuracy. So recall that our original motivation is that we don't just want to look at the answer accuracy because it doesn't imply whether the general chain of thought is also correct. So here we try to see if the proof accuracy is correlated with the answer accuracy. So how do we measure if the proof is correct? So a strict measure is that if every step in the proof is strictly valid, meaning that it's only using modus ponens, it's also atomic, there's no skipping step, and it's correct, meaning that it's not misleading. So this would be exactly the same as a ground truth proof. So we call this, so every step is the canonical step. So this would be a strictly correct proof. And then we also consider a more permissive metric, which is just checking whether every step is valid or not. So it could be skipping steps, it could also use misleading steps, but as long as every step is valid in the proof tree, that is fine. So in this figure, each dot is one experiment where we run with different sizes of models, and each experiment has 400 test examples. Okay, so then for each experiment, if we plot them by the label accuracy on the x-axis and also the proof accuracy on the y-axis, so we see that if you use this strict measure, the label accuracy and proof accuracy are not correct. So in particular, the label accuracy could overestimate the proof accuracy. However, if we use this more permissive metric, we see that they're actually quite correlated. So it seems that the model is indeed, at least in this synthetic scenario, using the general chain of thought to derive the answer. Okay, so the next thing we look at is how does the model size affect reasoning capability? So here we have GPT-3 models of different sizes, and the blue portion of the bar shows the proportion of correct output, where correct is measured by the valid proof accuracy. So we check whether the general chain of thought is correct. And the red part is the incorrect proof. So here, this is perhaps not very surprising, but clearly larger models perform better at this task. And in particular, it seems that just having a very large model is not sufficient, because both DaVinci and DaVinci 002 are 175 billion models. But we see that DaVinci actually struggles at task. The accuracy is around random, whereas DaVinci 002 performs very well at this task. So it seems that some supervision is still needed for this complex in-context learning task where the model really needs to learn these reasoning rules. Okay, so next we look at the proof accuracy versus number of hops. We have 1 hop, 3 hop, and 5 hop questions, and long proofs are still challenging for this model. So there's clear drop in accuracy. So maybe we need to think about better ways to compute iteratively at inference time, because clearly for longer proofs, it's a larger search space. The model will require more compute to do reasoning on this task, but right now it's not possible. Finally, we also look at the influence of real-world knowledge. So initially we have this hypothesis that maybe the model is doing retrieval rather than reasoning. So here we look at whether real-world knowledge influence the performance. So we test the model of fictional ontologies. So these are based on synthesized facts like hypotheses or non-hypotheses, and also false ontology that is counterfactual to the real world, and also true ontology. So the models are very good when we give it the true ontology, because maybe the model already knows that cats are carnivore and doesn't have to reason through the given facts. Whereas in fictional and false ontology, the performance drops a lot. Okay, and in the last set of analysis, we look at how do these large language models read them step by step. So recall that for each proof, we actually can annotate every step in this proof. So the first thing to notice is that the majority of the proof steps are actually canonicals, meaning that they're strictly valid. There's no skipping steps, and also it is not misleading. So this is every one step in the ground truth proof. So most of the proofs are canonical. So then we want to look at what happens when the model deviates from the ground truth. So these are the non-canonical steps. And to do this analysis, we look at the association between different types of non-canonical steps and the correct and incorrect proofs. So here, for these incorrect and correct proofs, we break down different proof steps by different types. So these are shown in the darker bars. And the first thing we notice that if you look at the correct proofs, there's a significant amount of correct proofs that would contain non-atomic steps. So they tend to skip steps just like humans do when we're verbalizing their reason. So note that this is not demonstrated in the in-context examples. So this is what the model generalized from the in-context examples. And if you look at the main types of proof steps in the incorrect proofs, they are misleading or invalid steps. So these are two main sources of errors. So then we also look at what's the cause of the incorrect proofs. Now we don't really know the exact cause, but we did a approximate study by just looking at the first error in the incorrect proof. So when it first deviates from the ground truth, what is the proof step it is taking? And so these are from a breakdown of the first error from small models to large models. So we say that from the smaller models suffer most from the invalid steps shown by the red bar here. Whereas as the model becomes larger, there are much fewer invalid steps, but instead the misleading steps is the main types of first error that's made by the model. So to give an example of this misleading steps, so suppose this is our context with a bunch of synthetic facts, and we have a query, we would like to prove whether Alex is fruity or not. And the model would prove generally correct proofs until this conclusion Alex is number. So far it's exactly the same as a gold answer. Now, given Alex is a numbers, we could just take this premise, every numbers is not fruity, and then directly conclude that Alex is not fruity, so this should be false. And this is what the gold answer is doing. However, instead of doing this, the model takes a wrong turn, and instead it takes this premise, every numbers is a numbers, which is still a valid step, but it is misleading in the sense that it's not very useful for our goal. And after that, the model produces an invalid step, and then it gives incorrect answers. It's just a downturn after this misleading step. So this shows that the model really struggles at proof planning or search, because here there are when there's multiple valid steps, ideally, if the model is doing this systematically, it should search both branches and then figure out which is the correct. But it seems the model is not doing that in this case. So then we also try to see if there's an easy fix. So one thing we tried is to generate a lot of samples from the model and then we rank them. And this is proposed in the self-consistency paper. So you can think of this as a approximation of the search procedure. So when you generate different samples, maybe they're exploring different branches and then they pick the correct one. But in this case, it doesn't really improve much over the baseline. And in particular, when we look at the, so sometimes the model did generate the correct outputs in one of the samples, but the log likelihood of that correct reasoning output is actually lower than some of the incorrect outputs. And we also try to put to demonstrate this search behavior by including one examples where the model initially explore a incorrect branch and then come back and go explore the correct branch. So we demonstrate, we include these depth first search examples in the in-context examples, but it also doesn't really improve the baseline significantly. So it seems that we probably need a more fundamental fix of this problem. Okay, so to summarize, what we learned about the chain of thought reasoning here is that first, at least in the synthetic scenario, it seems that the answers are indeed derived from the reasoning steps. So this chain of thought is not just a decoration, it's actually useful for the reasoning process. And also we see that most individual reasoning steps are strictly valid. So the model is able to learn these deduction rules either from pre-training or from the in-context examples, but locally, at least it is doing pretty well. But the models struggle with search and planning. It does not systematically explore different branches when there are multiple valid steps to take. Okay. So just to check the time, so I have 5 more minutes, I think.
Yeah, something like that. This is really interesting. So if you have more to say, please do go on.
Oh, all right. Yeah, so this is the first part. The second part may be less interesting, but I'll also quickly go through that. So we see that the model has this surprising generalization abilities. So, you know, even though it has some problems with search, which is also kind of expected because the model has limited memory and inference time. It doesn't have lots of additional compute. But still, the fact that they can learn this very complex in-context patterns that are unlikely to occur in the pre-trained. So if you look at our synthetic examples, I don't think you will see similar things in the pre-training data. And some of the model health ones are pretty complex even for humans, at least in the fictional scenario, but the model seems to be able to capture these complex patterns. So how is the model able to do this in-context learning just from the language modeling objective? So the one intuitive explanation, this is a figure from the original GPT-3 paper, is that maybe the model is seeing the in-context examples during training, and then if you just do sequence prediction or language modeling, this is kind of like a meta-learning process. The model learns to extract these patterns from consecutive input-output pairs. But if we think about it, the pre-training corpus rarely contains such clean meta-training examples. If you take a random Wikipedia article, we don't really see these input-output pairs. So our idea here is that why don't we directly train the model, you know, these meta-training examples organized this way to improve the in-context learning ability. So in this paper led by Yenda, we try to train a model to perform in-context learning, essentially. So using a pre-trained language model, we give it instructions, in-context demonstrations, and a query, and the parameters is fixed. So now we can generate a bunch of examples or in-context learning examples in the same format from many different tasks. Then we could fine-tune this parameters data on this in-context learning examples. Okay, and then to make an analogy with meta-learning. So in meta-learning, in the inner loop, we have a few examples from the task. We perform gradient descent through these tasks. And then in the outer loop, we have another gradient descent step to update the model. We have another gradient descent step based on the loss on this query example. So in gradient-based meta-learning, we have this bi-level optimization problems. However, if we use in-context learning for the inner loop, we don't need to do any gradient update when we're adapting the model to a new task on a few examples. So this is a kind of a supervised meta-learning approach where we just meta-train the model in the same way as we do supervised learning. Okay, and then we train the model on these in-context examples generated from many different tasks. And we see that using this in-context tuning improve the in-context learning performance over the raw untuned language model by 7 to 10 points on 2 different data sets. And also if we compare that with MAMO, which is a gradient-based meta-learning approach, we also see reasonable improvements. And we have the additional advantage, we don't need to fine-tune the parameters and have different sets of weights for different tasks. Okay, so the other nice thing that we're happy to see is that this also reduces model sensitivity to the prompts. So we know that the prompt engineering is an art. The model is very sensitive to, for example, instruction templates or how you verbalize the label or even the example order. So in practice, in order to find a good in-context learning prompt, we typically need to search for the right prompt on a large size of validation set. So this is not really few-shot learning because of this large validation set used for prompt engineering. And after this prompt tuning, we see that the model variance with respect to example ordering or example selection or instruction wording is reduced significantly. So this is something really nice that we wasn't really expecting from doing this in-context tuning. Okay, and to conclude, so in this project, we show that by formulating the training data in the format of this meta-training examples, we're able to improve in-context learning, but we didn't really answer the question of what are the properties of the training data that induce this in-context learning in the first place. If you think about the pre-training data, they're not really organized nicely in this input-output pairs like what we did. And this is something that we're currently working on. We have some initial results that suggest maybe the long-range dependency in the pre-training data is what causing or impacting the in-context learning performance. And there are other hypotheses as well, for example, the long-tailness of the data, and also there are papers showing that perhaps the transformer architecture encodes stochastic, can perform stochastic gradient descent through the forward pass. There are also interesting study on whether the model is learning from the in-context examples like in supervised learning, or it's really retrieving or eliciting the learned knowledge in the pre-training data. So I think there are lots of open questions how in-context learning emerged through the language model process that is exciting new research directions. Okay, so to conclude the talk, I think GPT 3.5 models are really fantastic. We're excited by all these amazing capabilities, but at the same time, I think there are a lot of work needed to unpack them. And in particular, we probably need better documentation of what this model can and cannot do beyond just anecdotes. Like most of the impressions of how this model works are from Twitter or some average number over many different tasks. And also important to disentangle the contributions of these effects from different factors, like models are trained through unsupervised learning, instruction tuning, also reinforcement through human feedback, and both the data and architecture as well as human supervision could be contributing to these facts. And again, there are lots of study needed to disentangle these factors. Okay, thank you. And perhaps I can take some quick questions.
Yeah, thank you. There's a question already. So at Pronto QA, why do you think self-consistency or DFS did not enhance the performance dramatically?
Yeah, so I think for DFS, it's possible that the model is not able to learn this search behavior. So especially if there are multiple hops, it may not be able to learn that consistently. Because I'm thinking the search required at inference time compared to what we were demonstrating could be much longer, especially if we're thinking this 5-hop questions. And also, I feel maybe a more fundamental limitation is it's unclear to me how the model would perform search at inference time. So right now, basically, the way that the model is doing more compute for more complex problems is through the chain of thought. So for every new word you're generating in the chain of thought, you can do one additional forward pass. But this is a very crude way of performing search. So if you compare that with the actual search module that have states that you could remember and branch out and then come back. So maybe we need some more explicit mechanism to support search at inference time.
Okay, we'll take one more question, which is, are there any cases of fine-tuning through chain of thought learning in a lightweight model?
Fine-tuning through chain of thought. Yeah, so I think actually for our in-context tuning, we didn't do that very large model. So I think we did it on GPT-2 size model, which is I think GPT large is like 300 million parameters. So I think it's definitely possible. So if you're willing to fine-tune that for a specific task, you can have a smaller model. But if you want to have general capabilities for many different tasks, scaling is important.
Okay, thank you. If you can stand by, I'm sure we'll have more questions during the entire Q&A. So thank you so much. It was really interesting. And you mentioned 2 papers that I am going to actually try and read. So now we have James do a quick intro. James has been at KAIST, I believe, about a year now. In the KAIST AI graduate school. And prior to that, he was at University of Cambridge for his PhD. And I'll just stop at that and let him go.
Okay, thank you for having me today. So yeah, I joined KAIST last year, and it's scary how quickly it's come up to be almost a year already. And I'll be kind of asking this question about maybe thinking about how we know what large language models know. So I'm sure most of you might be aware, I've done a lot of work previously on fact verification using external knowledge as evidence. And now I kind of want to start porting that task or that idea to see if we can validate the information which large language models contain. So last week when Minjoon Seo gave his presentation, he kind of started with this viewpoint that auto-regressive language models are capturing a lot of information through this language modeling task of next word prediction. This next word prediction task allows us to scale the language model to be trained on large data, which we scrape from the internet, for example, and through scaling the size of the model, the number of parameters, that we're able to capture a lot of emergent properties of natural language as well. So maybe we should be thinking about, does this next word prediction task really mean that we're truly learning the knowledge that we're from the information that we're training the model on? So this is a question I want to kind of investigate and dig deeper. And a spoiler is I don't have the exact answer right now at the end of this presentation, but instead what I'll do is give you some thoughts about the future directions, compare different approaches for understanding the knowledge which we have in language models, show some limitations, and then point to how we could solve this problem in the future. So it's 2023, and I wouldn't be able to do a presentation about AI without a screenshot from ChatGPT. So in this case, I was asking or giving the prompt to ChatGPT, why does increasing the size of the language model provide some performance increases for natural language? And we've seen for the last 10 years that the models that we're training have more and more parameters, and the mechanisms we're using to train those models as well allow us to train the models on more and more data as well. So the architectures like Transformer capture a lot of long-range dependencies, and there's a lot of other papers discussing the mechanisms in which those how transformers act as memory as well. For example, Morgaver's paper on the hypothesis that there's key value memory behavior in the transformer. So there's some knowledge which the transformer architecture is able to capture through this next word prediction task. And the question is, like, is that knowledge valid or accurate, or is it suitable for use by end users as well? So the LLMs have kind of been a very large paradigm shift in how we go about modeling in NLP. When I started my research, we kind of started with this conventional supervised learning setup where we took a model, we had a data set which we'd collected, and we trained the model to make predictions on that data set, reducing the error for that data. And most of the cost of that data set was associated with the collection of that data. Now, instead, where we've kind of moved to this pre-training and supervised fine-tuning paradigm, the cost of the modeling has moved from the collection of the data into the pre-training objective instead. So we scale the models to hundreds of billions of parameters, and this is something which is not feasible for most laboratories to complete and train themselves. And we can maybe do some additional fine-tuning or adaptation of that model with a small amount of labeled data. And more recently, since advent of GPT-3, we kind of do away with the need to have some specialized model. Instead, what we can do is provide instruction prompts or some other mechanism to the language model, so that the language model is able to reason with knowledge in context and use a textual description of the task. For example, how to translate from English to German could be one example of those. And this is kind of leading to large language models being used in many circumstances and situations that they weren't really designed or kind of thought about when people were training these models. For example, on LinkedIn the other day, we saw this job advert for prompt engineers even in legal settings. So if I'm taking my large language model and wanting to apply it to settings where there's kind of real world users and downstream applications with impact, perhaps I want to make sure that there's some correct reasoning and correct notion of factual knowledge within the large language model. So how can I check what the language model knows? And is this suitable for our downstream task? So I can already find some counterexamples of where the knowledge in the LLMs would have been correct maybe during one period of time, but is no longer correct now that the state of the world has changed. So the language model has some notion of world knowledge through this next word prediction task, but we find a situation where the model was trained on one period of time up until 2021, And then since that period of time, the state of the world has drifted, and the model is no longer able to use that knowledge for its inference. So as the state of the world drifts further and further away from the data that the model was trained on, we start seeing these errors maybe increasing, and the uncertainty that's captured within that model increasing as well. And this prevents us from asking questions to the model, such as what happened in the news yesterday, or who is the new president of South Korea, or even questions which might require access to personal information as well, as these wouldn't be captured in the pre-training objective of the language model. However, it's kind of critical to understand change in language, and this is one barrier to kind of this broader question of having language models which are factual stores of information. So if I take a step back away from large-scale language models, maybe I'd think about how I'd represent knowledge as a computer scientist. So let's put my computer scientist hat on instead, and think back to my first year of computer science. One way I'd represent knowledge would be this idea of a graph of knowledge, where I have subject, predicate, object, triples, which contain atomic units of information. And in this case, this is some function which gives us a representation that allows us to kind of deterministically say that the Nobel Prize in Physics was awarded to Richard Feynman, and the Peace Prize was not awarded to him. And because of the limited and symbolic state of the world, that knowledge is kind of hard-coded, it's captured well, but is very, very sensitive to the variation in spelling of the terms, for example, and it doesn't allow us to reason about things which aren't explicitly expressed in that knowledge graph, perhaps. So as we start asking our journey about what language models capture, perhaps this is a good starting point as well, thinking about how we could model this kind of knowledge graph structure and see whether it's replicated within large-scale language models as well. And so Fabio Petroni have this paper from 2019, where with the BERT-style language models, he was asking whether this probability of the mask token being Florence is kind of non-zero in the language model, and specifically whether Florence was the most likely token that the mask should be, for example. So we could take a knowledge graph and express it as these type of strings and use this as a way to prompt the language model and see what the knowledge captured in the language model actually is. So if I think this was done in 2019, maybe I could try replicating this now in 2023 and see what type of results I get. So do the recent language models have similar properties? Yes and no. So I've found positive examples and counterexamples where this works and doesn't work. So I take my recent language model, in this case I took T5 large, and kind of rephrased the question in a slightly different way. And instead I ask, instead of just taking the argmax, which was Venice in the case, I'm sampling 2000 times from the model now and seeing whether the answer appears in that list. So if I took this question and got Venice the first time around, that's the wrong answer, I find the correct answer was only in 6% of those samples. So the language model does have some association that Florence is the correct answer for this, but there's also a lot of influence from some other spurious correlation between Venice and Dante being, and that being the place of birth of Dante, for example. So all of these other cities as well, which are incorrect, have a non-zero chance. And there's many other answers like Paris or Milan, which also appear higher ranked than this correct answer. So this is just one example of a counterexample where this type of reasoning might fail. But maybe I could instead ask if the language model could act as a fact checker for this knowledge instead. So I could perhaps take this yes or no question and ask the language model, similarly with 2000 samples, whether Dante was born in Florence. And so now the LLM could potentially act as a fact checker for this answer instead. So instead of acting in a generative way, predicting which city was likely to be the place of birth, the language model here does a much better job of attributing some truth value to a fact, you think. But if I was to ask whether he was born in Venice, this also has equally high probability. And just to check that this property doesn't hold for everything, there are examples where Dante was born not in New York. So we see maybe there's some kind of spurious correlation between Italian cities or parts of his life, which allow Venice to be predicted equally as high. So using the LLM just in this way probably is fairly insufficient for validating knowledge, for checking knowledge, and maybe there's better things to do instead. So throughout my research career, I've been stipulating that if we're doing a task such as fact verification, the main task of the fact verification isn't to assign a truth value of whether something is true or false. Our goal instead is to find external evidence which we can trust, and then present that evidence in a concise and clear way to an end user. So if we can find some sort of evidence, then this evidence is like a user-facing abstractive summary of the information, and the user should be able to reach the same conclusions as the evidence given the same pieces of information. So this is the starting point I'm coming from in NLP, and I'm trying to think whether we can have some hybrid of the best of both worlds, exploiting knowledge within large language models or knowledge within textual sources. So why is textual sources useful? Well, it allows us to provide attribution of our answer to a specific piece of text. And hopefully when we see these changes in the situation of the real world, those can be much easily expressed in text just by rewriting some fact in an article or in Wikipedia. And in contrast, if we want to change that fact in the language model, firstly, that fact is attributed to probably many different neurons within the large-scale model, but also the change is likely to have side effects, and we can't fully attribute one specific neuron to one specific fact within our LLM instead. So if we're building a large-scale fact verification system or question answering system, what I might do as part of my pipeline is take this question and retrieve some information from that external corpus of facts from Wikipedia. And this set of facts is then used as some context, which the large-scale language model, NLU model, then uses and reasons with and kind of performs some generalization to generate an answer or output a label. So instead of maybe generating the facts directly, like I did with this knowledge graph setting, perhaps I could better exploit the training structure of the large-scale language model instead, and use the language model to generate the article, which could perhaps describe the background information necessary to answer the question. And that's exactly what recent work from Yi et al. Been doing with generation from LLMs rather than retrieval. So in principle, this sounds like a really good idea, because now you're generating a much more longer form article, which is more representative of the training data that the LLM was trained on, rather than this kind of question answering or fill in the blank style knowledge extraction. But there's some challenges of this as well. So how do we differentiate what is kind of useful knowledge versus what is the hallucination which can't be used? And this emergent property of generating the article really only appears when we have language models above 100 billion parameters. And for 10 billion parameter style models, or 11 billion, extracting useful information, which can be then used by downstream system, is still worse than just finding the information from the Wikipedia baseline. So this article generation property is something which is really emergent from the very, very large size language models. But instead of just trying to ask the knowledge directly, what we could do, or what this paper is doing, and what we could maybe use as a future direction for NLP, is evaluating the knowledge extrinsically through these type of tests and evaluations with more complex reasoning tasks, rather than just trying to simply probe the facts and extract single word answers from the model instead. Okay, so answer size, model size is one factor, which kind of gives us maybe useful information or useless information. But another factor which we also need to consider is popularity of entity as well. And so asking ChatGPT about myself kind of yields that I don't exist according to ChatGPT. But then if we change the prompt and ask a different question, or maybe in a different way, I can maybe find some information, but there's kind of spurious correlations again between my previous history or some other James Thornes which don't exist from what I've found by a quick Google search, and then papers which were written or maybe don't have anything to do with my history as well. So there's some inconsistency within the answer. Firstly, I don't exist, but now I exist where there's spurious correlations to other information. And whether this effect is attributed to entity popularity, I think is something which we should be further studying as researchers in understanding factuality in large-scale language models. So as I kind of draw to a close, what I'm thinking is we have two kind of core paradigms of how we train the model so far. We've been looking at, we started with conventional supervised training, and this was our classifiers and our kind of machine translation systems. And we've been able to incorporate external knowledge through open domain style NLP evaluation systems. But on the other axis, we have this, on the bottom of this chart, we have this distant supervision now, which our large language models are able to take advantage of. We don't need to have large numbers of these labeled data in order to train our models. And we also see on this horizontal axis, we have intrinsic and explicit knowledge. The intrinsic knowledge is what's captured within the model. And we see that with the very largest of scales, this large language model not only captures useful world knowledge, but it can generate full-length articles and exhibit very exciting emergent properties about information in the real world. But what we haven't talked about is this combination of using the large-scale language model with the text, which we've captured maybe from Wikipedia or some other source of truth that we trust as part of our reasoning. But this also provides a very, very exciting opportunity. And there's many retrieval augmented language models like RAG or Realm, which work well for this type of task. And one application of this is kind of, instead of trying to do some classification, we can maybe make corrections to misinformation using information, combining the generalization ability of large-scale language models with the memorization of having explicit information in text instead. So fact verification would use an article like Wikipedia to assign a label, like refuted, to this claim that brown spiders don't bite. But the task of factual error correction is instead to rewrite the claim with real information such that that original claim now becomes supported by evidence. So we see a change of label from verification, so a change of task from verification where we predict one label to correction where we change the claim such that the label also changes. And these type of retrieval augmented language models allow us to kind of condition the generation such that we can generate different answers or different outputs by using different text during the inference of the models. So if the model is truly trained to understand and reason with text, then to use that text as part of its generation, then by changing the information in the text, then we can change the output that the model generates. And we can synthesize this with a training where we depend on the text for generation. So going back to this landscape, it kind of gives us a load of open questions about the different types of models that we've been using in natural language processing and the open questions around it as well. So if you take supervised classification or some generation task without external context, imagine taking a squad classifier and not using the context. Your model won't do too well. So that gives us a real question in the top left corner here, why we should be using context as part of answer generation. And these explicit knowledge from Imagine Squad, for example, that allows the model to find the right information from the input it's being given and use that information in order to generate a correct answer for the user. On the bottom left, now we see that instead of just giving that article from Wikipedia to the model to reason over and to extract the context, we can now generate that context instead through the new advances and very, very large language models, and recite the Wikipedia context from the memory that is captured within the large-scale language model. And finally, in the bottom right corner, we have this idea of the retrieval augmented models, where we find the information from that external source, but we incorporate that into our prediction as well. And I imagine a future where in NLP, we're not just trying to generate and understand the information that the knowledge is captured within the language model is, which is expressing information, but we want to be able to use that knowledge and combine it with extrinsic knowledge in downstream tasks, such that we're able to take the best of both worlds. And then what I imagine Professor Minjoon Seo will be talking about in his next talk will be about editing the models. So if we can use that external knowledge from somewhere like Wikipedia or an article we trust, can we then use that to update our model as well? So I have a lot of open questions, and perhaps this is my take on a future direction of where we can incorporate knowledge in NLP. So there's a lot of open questions, and I'm looking for people who are interested in studying these questions together with me. Some of these questions are about self-consistency. Can the LLM be verified against itself? External validity. So can the LLM be verified against textual knowledge from a different source? Can we list and enumerate all facts for a specific entity? And how do those change with a different prompt, perhaps? And how do we study the effects of entity popularity in the large-scale language models? So I started my career with using fact verification for checking news and reacting to emergent information threats. But now I'm kind of like changing my direction to instead ask much more deeper intrinsic questions about the knowledge in our models. So how can we use what we've learned from fact verification to build further trust in our models and make sure that they're accountable with external information? And that's my take on knowledge in LLMs. Thank you.
Okay, let's take a couple questions before. Yeah, okay. And by the way, this is another great talk. Thank you so much. And I think we're building this entire series of talks today is just building up to something really, really interesting. First with, doing something logical or trying to do something logical. And then now we're talking about knowledge, and we're going to continue to talk about knowledge with Minjoon's talk in a few minutes. So the first question is, Bing and plus ChatGPT a similar idea as a generative model combined with fact checking? How could we further check the truth of external information?
Oh, that's a really good question here. So is Bing plus ChatGPT an example? So actually, I don't quite know how the Bing plus ChatGPT works. And because it's a commercial product, I think Microsoft are very loose on the trade secrets that they release and tell us about. I can imagine there's a lot of different approaches you could do this. You could either do this kind of knowledge incorporation pre-hoc, or you could do it post-hoc. So you could use the knowledge to condition the generation, or you can do some generation and try and condition attribute what you've generated to an external source of knowledge. So the second would be more like the fact verification style models, where we try and find evidence to validate what the model has generated. I think that's a really good research direction. But another more interesting research direction is the retrieval augmented model as well, such as RAG or Realm, where you find the information first and use that information to condition generation. So I don't know what Bing is doing just yet, but I'd imagine it'd be one of the two.
Yeah, on my tries, it doesn't seem to do so well on fact verification, just my personal experience. So the next question, what sources will be proper external information, and how can we collect the external info sources? Oh, I'm sorry. Before that, does the prompting accuracy increase with model size?
And this is still kind of ongoing work with the sampling, which I've been doing. So I don't have an answer for that just yet. But in some kind of, I wouldn't say this is a generalizable trend, but I found different behaviors depending on different model sizes from the examples I've tested with so far. But I don't know like exactly how the answer accuracy would depend on the prompts just yet. We definitely know from other work that the large language models exhibit better kind of instruction-driven behavior with both size and the instruction fine-tuning. So we need to make sure that the models are adequately trained for that task.
Okay, so what sources will be proper external information, and how can we collect the external information sources?
Yeah, this is also a really good unanswered question right now as well. So in NLP, we kind of cheat a bit and we just use something like Wikipedia. The reason we use Wikipedia is because the external information there can be saved as a snapshot. Wikipedia allows us to download all that information, and we're allowed to distribute it as well. So we don't have any, well, because the information in Wikipedia is Creative Commons licensed, we can distribute it without having to pay royalty, for example. So if we want to build a much wider corpus, maybe with medical journals or some other sources of information that we want to use, then we have a lot of challenges beyond just the technical challenges when we want to use that external information. And we can imagine scaling up to something the size of the internet. If we take common crawl data set and try and validate the predictions of our large language model against something like common crawl, we probably need to build other methods to evaluate the factuality of the external information that we're using as well. And that may lead us to some type of chicken and egg situation where we're trying to validate the knowledge against knowledge which we can't trust either. And this is a kind of big question still, and one where we don't have the answers. So I can imagine the future of fact verification having to incorporate this knowledge and also deal with conflicts. And this is a direction I want to study in the future.
Okay, LLM pre-training is done on many massive data sets with an average epoch for each data set equal to 1. That means the model has not seen most sequences of tokens more than once. So knowing the learning rate of most models is small, how can the model remember the input data token sequences as knowledge stored in the parameters?
Yeah, I think this might be better answered from Kyung-Yeon Cho's talk last week with some indication of the lookup style tables in the LLM. But when we're training our LLMs, we're taking samples of text. We take a few hundred tokens in context, and we're building these word by word associations. So while we may not be reciting text verbatim from the training data that we've used, we're still learning some of these associations between common words, and that might be one of the reasons.
Okay, so thank you again, James. That was a great talk. And we have Minjoon. Do we have Minjoon? Okay, yeah. So a quick introduction about Minjoon. He did his PhD at University of Washington. And I think he was at Naver for a couple years before coming to KAIST. And he's also at the KAIST Graduate School of AI, has been there for, for a few years. And it's great to have him talk to us today about continual knowledge learning for language models.
Thank you for the intro, Lise. So actually, I changed my title a bit. The abstract should be about the same. It's just that I wanted to talk about both, well, knowledge learning and also how we can access that. So it's a bit more, I think, broader than what I said previously. But thanks for the intro again. So I'm going to talk about how we can update or access knowledge in language models. So here. What I'm talking about is that we know that language models are known to contain the world knowledge. So they're not just language model in that they can predict what the next word is. They can also contain information about the world. And I think that's exactly how, as He and also James talked about, we are using language models like ChatGPT to do our daily tasks, because otherwise, if the language model doesn't know about the world knowledge, then apparently we cannot do that. So that's been, I think, and I think surprisingly, this fact was not so obvious like 3 years ago, I think. Remember that back then we were using BERT or similar pre-trained language models, and then we were using them for mostly more of well, understanding the language in a linguistic or more of a semantic manner. But we were seeing a few signs that language models contain the world information, and I think nowadays it's quite well. I think relatively everyone agrees. So it's amazing that how the things changed so fast in last years. So given this fact, language models contain the world knowledge. I think there are two really important things that we need to be aware of. One is that the world changed very fast. So we have trained language models, for instance, with the data up to like say 2021, like ChatGPT, but then a lot of things have changed since then. And then if we're using just language model to do our daily task without any, say, reachable augmentation, then we clearly want the language models to be aware of these changes. And then our argument was that it is really important to efficiently and safely update the knowledge inside language model, especially without retraining it from scratch. Well, because if you retrain it, then it's going to be very costly, and that's very bad for everything, including the environmental effect. So, so in the first part of this talk, I'll be talking about how we can do this. How can we update it with the two recent papers at iClear and EMNLP, and by Joel and Sanghyun Ye. And the second part will be, I'll be briefly talking about, let's say we now have the language model with this updated knowledge or any knowledge that we are interested in, and then how can we access that information inside language models? And when I say access, then you might be thinking about, well, wasn't that more of a retrieval thing, which is you have some encoder, you map the document in question to the common vector space, and you're trying to do similarity search. And yes, that was, I think, really the traditional way of accessing information. And I'll be briefly talking about what the difference is, what we think, and what can be leveraged from using the language model instead of this canonical retrieval mechanism. Let me first start with the first part. So this will be our last year iClear paper, which is on how we can learn knowledge with language models. So the motivation is, as I mentioned, suppose that, let's try to simplify this into more of a, well, mass language model, although you can think of this as a more of an autoregressive language model too. But then let's say you're given the sentence, Barack Obama was born in and blank. And well, we know that the large language models can guess this correct. And it's not just about syntactic or semantic information, because if it was that, then, well, we cannot really know what the answer is. But then the language model knows that the answer is Hawaii, well, because it has learned that from pre-training or the language model training. And apparently, this is very useful for various domains, especially if you want to use language model without any retrieval augmentation. And we know that, of course, this has a lot of issues like hallucinations, everything, but then we're working on that, right? We're working on that to, if we can do these things, well, I'm not sure, I'm not saying that it's good to remove retrieval, but then still, I think it's a good direction to make this as accurate as possible with just language model. Then maybe we can do retrieval to make it even more accurate. So we're trying to see if we can do that. But But then another way to put this is that, Barack Obama was born in Hawaii. This doesn't change. This is a fact that doesn't change. But there's a famous soccer player called Cristiano Ronaldo. And if we ask where he plays, well, it changes, right? Because he was playing in Juventus before, but now he's back at Manchester United. And actually, he was at Manchester United like 10 or 15 years ago. So things change and things can come back. And that's really the problem with the large language models. If you're using large language models only for, trying to predict these factual things. And we'll see cases where if we use this for other facts, then we're not even sure what the answer will be because of the language model being trained in past data. We have never seen, if we train up to 2019, then we have never seen what has happened in 2020. So in this work, we are mostly focusing on how we can divide the facts inside language models. And we actually made a distinction between invariant, updated, and new knowledge. Later, we actually think that updated and new are quite similar, but anyways, invariant knowledge is something that will never change. Updated knowledge is that something language model already knows, but that might have changed since then. And new knowledge is something that never encountered by language models during pre-training. And then this is a good point that I wanted to bring up again. Even so, people might ask, why do we need this if we can have really good retrieval and we can actually bring the actual documents? Well, the fact is that even if we retrieve a good document, it has been seen that if language model is strongly believing in certain direction, then it hallucinates, even if it's conditional on this retrieved documents. So it is certainly, again, emphasizing that even if we are using retrieval augmented models, it is important that large language models are also very true to what the world is right now. The more the language model is updated with respect to the current world, then the less hallucination we expect in general. And we want to note that there are quite several related work in this direction. For instance, there is a fine-grained knowledge editing that has been explored in last 2 years. Actually, there's a lot of work in this direction. But then, the main motivation in our case is that we of course can do this relatively easily if we can just retrain everything on Wikipedia or Common Crawl Jump. But then that would be very not possible. I mean, that it's possible, but it's very not doable if the knowledge gets updated very frequently and it's computationally inefficient. Then we can think about pre-training on the updated data, which is maybe just we're talking about the new additions to the common crawl, or it could be those that are changed, but then this now has a problem of catastrophic forgetting. So what that means is that while it tries to learn what's new, then it now forgets what has learned before. So that's really bad because now your language model doesn't know anything. It doesn't remember things correctly, what it learned previously by just trying to update it with the new knowledge. So that's actually not entirely new problem. It has been tackled in the I would say image domain, especially what they call this is continual learning. So it was relatively synthetic setup though, that they have a series of tasks. They start with, for instance, image classification and then move to other tasks like image detection. And then later they find that if you continually learn new tasks, then you forget to do the previous task. Here we call it also continual learning, but it's important to note that there's a big difference that we're not trying to learn the new task. We're trying to learn new knowledge. So that's why we call this call this continual knowledge learning, because previously it was more about continual task learning, but here it's more of a actual fact or knowledge, specific knowledge that we're talking about. So in this work, that what we were our main contribution were, first of all, we wanted to have a benchmark data set that can differentiate between different types of knowledge update. So it can be either, well, not knowledge change. So either it can be a new knowledge, or it can be updated knowledge, or it can be invariant knowledge. So the point was that, well, during pre-training, we learned a lot of knowledge, and of course, many of these knowledge pieces are invariant. And what we want to see is, let's say that we had some pre-training continued with the new recent corpus. Here, of course, it's 2020 to 21. And what we want to see is, okay, after pre-training on this, continued pre-training on this corpus, new corpus, does our new model is okay with the invariant facts? But then also the model can encode the updated or new knowledge that's only existing in this new corpus. So this is an example of how invariant lemma and updated lemma is defined. So for instance, invariant lemma, note that how we test this, how this benchmark is made of, is not like question and answer format. It's more of a fill in the blank, following the lemma, which is a previous work that does this kind of fill in the blank to evaluate how much knowledge the language model has. So things like, for instance, iPod Touch is produced by Apple. It's something that will not change. Well, unless I guess maybe company name changes, but the Sharon Cuneta show was created in Philippines. This probably doesn't change as well, but there are some other kinds of facts that change. For instance, who is the prime minister right now? There is a new lemma, which is that what the language model would not be able to answer previously, but now has answer because things has changed since then. And we actually also made an easy ones here. So we have a new lemma, but then a part of it is easy one. The point is that the new lemma, well, this is human created. I mean, it's actually not 100%, but then at least the new lemma is mostly human created. But we wanted to also scale that up with some noise. But it's usually then it's much easier because of the noise. But then we made that so that we can have some easy training. And we also wanted to measure how much it forgets with respect to how much it can acquire new knowledge, and also how it can react to the update knowledge. So we're trying to measure the ratio between these two. We call this a 4 metric. So now to the method. So how can we actually update the how can we continue pre-train to update the knowledge? So most, of course, straightforward way is to continue pre-training. That will be the baseline. But then, as we will see, that's actually not that good. So we also explored 3 other methods, which has been explored in the previous continual learning literature in the continual test learning. And those 3 are mostly regularization, parameter expansion, and rehearsal. So rehearsal is also known as experience replay. So this is very straightforward. As you train on the new task, you you actually also give the examples from the previous tasks time to time, so that the model will not completely shift to the new task. So we can do a similar thing in this continual knowledge learning setting. But then, of course, you might guess it's a bit different because now we're talking about specific facts, and it's not like we cannot, of course, rehearse everything we learned in the pre-training. So there is a bit of difference. You can expect that this will not be as easy as in the continual test learning. There's also parameter expansion, which is that you're adding new parameters to learn new things, and you can use now adapters here. I think right now the most efficient adapters are usually LoRa, you can also use less efficient adapters like K adapters. And there's also regularization trick, which is basically trying to prevent the model from being too much different from the original model. So we are penalizing the difference between the current model, which is being trained, and the old model, well, based by measuring difference between the weights. Well, I'll just give you the conclusion. It looks like the parameter expansion is performing the best in general compared to the other regularization rehearsal method. And this is a bit different from what people know about the continual task learning, because, well, I called it continual learning here, but then just trying to say this because to have a good comparison between those two. So there is a difference between continual task learning and continual knowledge learning, because these two methods, especially rehearsal, has been very effective for continual task learning. But when you're trying to do continual knowledge learning, this is not so effective. FUR is quite high. Whereas if we use some parameter expansion methods, adapters, we have quite low numbers. Especially we're also testing with the T5 modular, which is kind of extreme of the parameter expansion, that we actually not just add adapters, but we add new T5 models as we train new ones. And of course, it's very not parameter efficient, but then still it's very effective in terms of accuracy. So, well, our conclusion was that, oh yeah, we have to actually expand parameters to balance the stability and plasticity, which means we don't want to forget too much, but that we also want to be able to attain new knowledge. So there is some graph that's showing you that apparently, well, there is a lot of forgetting happening if you do training. But then also one thing was interesting we found here is that if you see the same data repeatedly, then it actually causes more forgetting. And it's actually quite relevant to, I think, recent findings in, well, recent arguments in large language model training, that it's important to reduce the duplications, or they call it deduplications, for the language models not to overfit to this data. So I think there are some, I think, interesting common findings that I think duplicate data is not that good. So we'll probably skip this. I think it's quite straightforward. What we're trying to say is that the adapters or the knowledge parameter expansion is really good. Okay, so I think I maybe spent too much time on it, but then I think the rest of the talk will be relatively brief because we know we have a good understanding of the first paper. So the second paper was mostly focusing on the fact that, oh, this is great, but then, well, I think this is great in terms of trying to evaluate how good a method is, but in practice, especially for industry applications, we probably want to update language models continuously. So we don't want to probably have language model that just sticks to, say, for instance, let's say consider Llama, which was trained like a few weeks ago. And we probably want to update that continuously, let's say, like, I don't know, once per month. Then, well, how can we know that the language model, when we're doing continued pre-training, it's doing well with respect to attaining or getting new knowledge? So we wanted to create a benchmark that's more of a ever-evolving or lifelong benchmark, basically, for these ever-evolving language models. So the main motivation was, I think, the main point here is that we don't have such data set, but then the also important part is that, yes, we create a data set in the previous paper, but then that's very human effort driven. We cannot do that like every month. That's very impractical. But how can we kind of automate this with the existing, well, data sets or existing, I would say, well, existing how the world is going right now. So when I say how the world is going right now, what I mean is that we know that the Wikipedia is getting updated regularly. And we also know that the Wikidata is the structured form of the Wikipedia. update regularly. So, and of course, there's an alignment between them. We can try to make that. Then here's a simple but quite effective idea. If we can align them, then we can also have evaluation data created from this wiki data, and we can use this Wikipedia data set as the pre-training or the language model training data. And then we can, for instance, let's say we have a October Wikipedia dump, and then we have a new dump in November. We can measure the difference. Unless the language model was pre-trained on this, continue pre-trained on this difference, then can we actually also compare difference between the October and the November wiki data, and then create the evaluation data so that we can know whether the knowledge here has been correctly updated, and also the invariant knowledge has not been forgotten in the new model. So that was the basic idea of this part, and I think the rest is quite clear, right? We basically were trying to create a very carefully engineered mechanism to automate this without any human efforts. And as a conclusion, what we found is that we can actually if we use just a difference data instead of entire data, then we can actually achieve a lot of computational efficiency here, 12 times less computational cost. So it is clear that if we want to actually probably, if we want to have an ever-evolving language model, that we want to train language model this way. And also we see that there is a similar or better perplexity, which means there is no performance degradation by doing this way, compared to just trying to train scratch from every time. Yep, so we did that. So it's lifelong, and we can see a quick example. I'm not sure how I'm doing regarding the time, but probably I don't have much time. Yeah, so I'll just end quite soon. So yeah, I think so. I guess then okay. So as you see here, there's a data set of LifeBank. This is coming from the what was it? I'm a bit confused. Yeah, so this is actually diff data. So as you see in the Wikipedia, you see that there was a change quite recently. There previously was September 2021, has 520 branches, but then apparently it has updated to 536. This is a diff between the two dumps. So we know that, okay, this has been an update, but sometimes it's actually entirely new information like this. It's exactly git diff, right? You have a new information, so it's more of a new knowledge than updated knowledge. So that's how we constructed by looking at these git diff and if it's addition or update. So we create that automatically here. Well, it's automated way, so we can also create this continuously as the Wikipedia and Wikidata gets updated. So I'll probably skip this part. So at the end, what we're trying to say is that, oh yeah, it's still the same story. LoRa or these adapter methods work usually really well. Yeah, as you see here. But then, and it's also actually working even sometimes better than the full training from scratch. So what that means is then, oh, there is no really reason to train from scratch. It's better to probably update that with new adapters. But of course, we're not saying we cannot extend that argument for indefinite number of months. We only tested for a 4 month, right, from August to December. So it might not be true after that. Probably that means that we might want to do full scratch from the from training from the scratch maybe every year, but then maybe we can do the updates every month. Okay, so we're talking about also another stability plasticity trade-off. So yeah, so we see that it's not actually, it's as we see again, we know that the adapter is usually doing quite well here. It's lower the better, by the way. This perplexity is lower the better. So the green ones are usually the best, which is adapter. Yeah, I'll skip this. So actually, I was going to talk about this too, but I'm running out of time, so I'll probably skip that. So I think the conclusion was that I wanted to talk about these two, but I ended up only talking about part one because of my bad time management. But then, yeah, maybe later if I have time, or you can also take a look at our paper. Then after we have encoded information in the language model, then the next part is how can access that. So that's in this Hyunji's paper from MLP 2022. Okay, thanks a lot.
Okay, thanks. You know, it's because you've done so much wonderful research. I should have given you like 45 minutes. And I'm sure
It's about that time, yeah.
I'm sure Ha and James also have other work that they've done that they'd like to also talk about. So it's just you know, we have so many wonderful students and, you know, their wonderful papers. It's actually happening for the entire field, right? There's so many good new findings coming out like every single day, it seems like. Are there questions for Minjoon and updating the knowledge? Okay, then.
Yeah, it's really good question. That's right. So basically, that's really good question. That's actually the biggest bottlenecks of these parameter expansion, as you say. If we just update once, then that's fine, right? But then if we update multiple times, then we have to add adapters that many times. Even then, that's actually much well, I would say. Oh, so okay, you were asking how we can add adapters multiple times after the first time. So yeah, well, so to be more exact, in the temporal wiki, the second part, we only added adapter just once. So it's not like we're adding one more adapters. It's starting from the pre-trained model and then just using one adapter for that. But then we might have to add more adapters. And in that case, it's not probably that clear how we can do that. I think depends on the architecture of the adapter. If it's LoRa, then it could be that we can just add one more adapter in parallel.
Yeah, I had that same question. There's another question. Are there any insights why there's discrepancy between continual task learning and continual knowledge learning? For example, why methods in continual task learning do not perform well in continual knowledge learning? Yeah. Okay,
good question as well. So I think the biggest difference is that when we're doing continual task learning, it's more about the I would say kind of meta knowledge that the model has to acquire to do the task. So that's kind of common among all the examples in the task. So it's relatively not so bad if you can just do the experience replay. But then experience replay would not work in the knowledge because unlike these meta knowledge for the task, well, the knowledge for each fact is not generalizable. So what I mean is that let's say you experience replayed where Barack Obama was born, but then that would not help you to actually retain the knowledge about where maybe another president was born. So it's more about, I think there is not really much common knowledge between these examples. I think that's one of the biggest reasons why the experience replay doesn't work. I think regularization is kind of in a similar manner, but then yeah, we're not too sure, to be honest.
Okay. Third question: how can we measure and quantify unintended side effects of the model when fine-tuning?
Yeah, I believe when you're saying fine-tuning, you're talking about continued pre-training, right? Or was it the after that? Just a quick question about that. Okay, that's right. Okay, yeah. That's true. So I think that's really important point. It's a good question. So we were trying to measure the whether knowledge is not being forgotten, but then as you said, maybe that will not result in losing other ability in the language model. So that we haven't really tested or evaluated. So I think that's really important thing that we also need to measure, which we have, I think, overlooked. Yeah, thanks for the suggestion.
Oh, quick last question. What's the advantage of continual knowledge learning in contrast to retrieval?
It's also a really good question. So yeah, I will just give you, I think, kind of really short answer. I think number one, I think even we retrieve really well. The point is that because language model can hallucinate if it has very bad knowledge inside it. So we probably want the language model to be also aware of the information. So it's not like we can just entirely depend on the retrieved documents, even if we're using it. And number two is that sometimes much more. It's like, I think, kind of similar to ChatGPT in that it's much more. It's simpler if you do not use retrieval. It's probably not as accurate. So in some cases, maybe it's better to just use a language model without the retrieval augmentation, depending on the application, I think. But yeah.
Okay, so thank you again, Minjoon, and we're going to move on to a panel discussion, which will be a little bit more general than like these specific talks. And I'm thinking, so we are having this all videotaped, recorded, and I myself feel like I should watch this again to at least look at the papers that are mentioned, because there's so much detail in your talks that that we actually really need to dig deeper into, and because of time constraints, obviously you couldn't go into all the relevant and important details. So in this 30 minutes or so, we're going to talk about sort of the future of NLP and also collaboration that we can perhaps do among ourselves and kind of more generally with NYU and KAIST. So my first question was, have we solved NLP? And the answer, of course, from your talks is that we haven't solved everything in NLP. But I guess perhaps what everybody is kind of thinking, are we heading in the right direction? So with these neural net models, with these autoregressive pre-trained language models, the models getting bigger and bigger, and then we do, in context learning, we do adapters, we do, all these other things to correct for some of the inherent problems of these pre-trained large language models. Is that the way to go? Or do you think there are sort of major paradigm shifts that need to happen for us to really tackle NLP? So who wants to go first? James?
Yeah, sure. I'll make a starting comment, I guess. Like, I think we're in the right direction, yes. But every time we take a step forward, we start revealing new questions about the type of models. And so it feels like as we develop more and more of these techniques, we have more and more questions about how they work and whether it's the right technique for the task we're trying to model with NLP. I feel trying to model everything with a single very large language model is probably the convergence we're heading to. We've seen that the transformer architecture has kind of been universally adopted in knowledge-intensive NLP tasks, and other NLP tasks are kind of being applied with transformer as well. But whether that's the right mechanism or architecture for every task is still a big question, and maybe it's not.
Yeah. Did you want to add something?
Yeah, so I definitely, so I do think large language models are going to be around for a while. And you mentioned there may be another paradigm shift, and I also think that there will be a paradigm shift, but it's very hard to predict beforehand. But I can maybe say something about the limitations of the current large language models that I see. I think maybe from both James and Minjoon's talks, it seems an obvious limitation. It's unclear what's the best way to accumulate knowledge in this model. So one is, of course, that the world is changing, but even aside from the world knowledge, from a user perspective, when using the model, of course, I can prompt it to perform different tasks. But after the prompt is gone, the model go back to the original state. And next time I have to somehow teach it this additional things where it performs some task. Whereas for humans, it seems learning a new task is pretty, or obtaining new information is relatively easy, or at least less cumbersome than updating the parameters of this large models. So there's maybe a better way of accumulating knowledge. It could be a separate memorization module or retrieval module, or it could be some new architecture. So that I don't really have a good sense of. Yeah, but it seems a better way of accumulating knowledge would be an important feature.
Yeah. So to Minjoon, with the same question, right? So since you are talking about updating knowledge or updating language models with new knowledge, what do you think? Are you satisfied with what we have so far?
Yeah, actually, I have a really, I think, very high agreement with the other two. Well, because I think what we are seeing these days is that we have discovered or made very good function, which means we can input something and we can have a very accurate function that can output what we want. And I'm not saying function is like a simple thing. It's more, maybe humans are functions too. So I think when I say functions, what I'm saying is that we have a very good input to output mapper. And I think that the biggest problem here is then, well, because of the complexity of computational complexity of transformer, we cannot really have a very large input. So it's like right now, probably the like Meta's Llama has up to like 200 tokens. Maybe the ChatGPT or GPT has even larger number, but then probably cannot get like hundreds of thousands of tokens quite soon. And it's gonna be very costly anyways too. So my point is that I think it's going to similar well, conclusion. I think the reason for this is, of course, humans usually do not get the input at once, a lot of input at once. It's more of a, they get like a small chunk of input and they somehow store that in their, I think, brains, and then get the new inputs. And then now humans become new functions, kind of, I think, that updated functions, right? And then I think that's something that we haven't been able to do as well compared to other achievements. So I think that's probably and something that we haven't been able to do well yet. So I think that's probably one of the next big, well, I would say, challenge. And also, when that happens, then we might see a language model that has very good contextual awareness, and that can be, I think, very capable and also very, I think, very, I would say, yeah, it'll be quite scary too. Yeah.
Yeah. So that actually, I will ask you to continue with the next question, which is about the major challenges. I mean, you sort of mentioned at the end here, so contextual knowledge, or like, do these language models know about context, and can they, or okay, so another thing is we have been talking mostly about knowledge, what language models know and do not know. What about other challenges, right? So there are other things that language models don't know how to do, like reasoning, for example, on like temporal reasoning or any other types of reasoning where humans tend to do pretty well. Abstraction is another area where, language models don't seem to know when and how to abstract it. And you may be thinking of other things, right? So the current NLP models are not able to do, and it's not immediately clear to us how to tackle these really important and difficult questions. So what do you think?
Okay, should I go first, or
Yeah.
Okay, I see. It's going the other way then. Okay. Yeah, so I think it's a really difficult question, but I think my answer is similar to my first answer, in that I really feel that the biggest bottleneck right now of language models is actually their inability to capture very large context. And I think that's exactly because, well, language model, first of all, it's trained on very large web corpus. And I think in some sense, well, because language model is trying to pick next word, and that next word has been actually created by some human, right? It was written by some human, but different individuals. So it's like more of a kind of, well, language model is trying to mimic what all those people who wrote the web corpus are kind of thinking, right? So in that sense, then it's learning the common thing very well. which is like linguistic, semantic informations, as well as even like really relatively, I would say, simple or even complex reasoning. But then it's not certainly doing, it's not still certainly not capable of capturing contextual information as well as humans. So I think that's exactly the biggest challenge right now. Yeah, so which I think people are really interested to. Yeah.
Yeah. So, what do you think? Can you think of other major challenges, or how we can tackle those challenges?
Yeah. So maybe I'll first comment. I think it's really good to bring up this analogy or abstraction thing, and I'll also say some other challenges that I have in mind. Yeah, so actually we have some projects on creative text generation, like writing poems. I find large language models are really not impressive on creative writing. And also chat with someone who working on music generation, it seems there it's all about analogies, and the models are not great at that. And I feel for this in this creative domains, when we want to produce analogies that are very abstract, like love is soft. This is a common analogy, but like, why is that soft? And this is really connects to perception or grounding in a different modalities. So I feel perhaps for those analogies, we would need multimodality, or at least have the model be able to interact in the real world to be able to connect these different things and build these analogies. Yeah, but anyway, I think that analogy is a really good point, and I don't think large language models are being good at that at the moment. The other challenge that I was thinking is it's related to active learning, but more generally, is the model, can the model have some notion of what it doesn't know and actively find evidence or performing or designing experiments to figure something out? Like for humans, perhaps I know that to answer this question, I'm lacking a piece of knowledge and I can try to find this information. Or I know that I'm very uncertain about certain hypotheses, but if I do this additional experiment, I'm able to figure that out. So it seems right now the large language models are passively going through large amounts of data. That's why it's kind of absorbing all this knowledge. And perhaps it could also find some reasoning patterns and deduce some new knowledge, but it doesn't seem there's an obvious way to use these large language models to actively testing certain hypotheses. Like it's not even clear whether they have some notion of uncertainty and hypothesis.
Yeah, great points. James, what do you think?
I was going to say very similar things to Minjoon. I have a couple more though up my sleeve. So I think another challenge, especially around the knowing what you don't know, is attributing what you know to a certain source as well. So being able to understand what factors in the training data of the LLM were responsible for or had an influence on the model generating a certain output, for example. This is very important for establishing some traceability and explainability of the model. And then especially around things like music as well, understanding high order structures is really, really important, especially if you ask the model for generating things like guitar tab or music notation. If you ask ChatGPT to write a guitar tab in a certain key, it'll pick wrong chords, for example, or it won't generate chord structures properly in guitar tab because you need to reason over like 6 lines of text for the string. So it's not really capable of doing that. It will generate tabs, but they're just not accurate. And finally, for this high order context, it's probably needed as well for doing this large scale database style reasoning over text as well. If I was to ask the model to list all athletes who participated in an event, for example, there might be 20 or 100 or 1,000 names, and those need to be recited from text or from memory of the LM. But when you're generating and decoding that list, you want to make sure that you're not duplicating yourself and we're not hallucinating new names. And then if I wanted to do some computation over that as well, for example, counting how many participants there were, the model, again, needs to have some capability of understanding higher order structure.
Yeah, so let's now try to, and I'm sure we can think of many other challenges that remain in NLP. Creative writing is an excellent topic that I've been thinking about also, and reasoning over other types of data, multimodal grounding, all these really great challenges. Do you think that these will be solved in, let's say, like 5 to 10 years? Are we, since during the first question, most of you seem to agree that we are heading in the right direction, and then we have these challenges, but are they going to be solved in 10 years? And if so, what will remain? What are the toughest challenges, do you think? Or do you think we'll be, as a community, we'll be done with NLP in 10 years? James?
Yeah, well, when I was writing my PhD thesis, I was kind of hoping that, well, I was kind of toying with the idea that if I was able to write an AI that could generate a thesis, then that should be enough for my thesis to be passed, for example. And it feels like now something like ChatGPT is getting close, but I still think in 5 years, we'll see new developments in AI and machine learning and natural language processing. And that will ask us questions about how we can apply those models to new settings. And then in those new settings, we'll realize the limitations of the models we have. And that will give us new research questions and new things to study and to develop. I think as the more and more people are working on these problems, we have more and more ideas. And this is really good because this gives us more questions to ask about which of these ideas are the right ones for a certain task, what the limitations of these ideas are. And it feels like there's a lot of new work, but there's a lot of new problems to solve as well.
Okay, Minju, what do you think in 10 years?
Yeah, it's actually something that I think about a lot these days, to be honest. Well, I think in two ways. One is that, of course, out of curiosity of, well, I think everyone here is very curious about and also want to contribute towards better AI, how good it can get. To be honest, number two is actually, well, do we really want a good AI? That's also the important thing too.
Yeah.
Well, because I think I honestly am seeing a lot of well, people always, of course, I think say, well, better AI makes everything more efficient, and also it's just better world. But I think for some people, it's very well, not that good. I think it's not really NLP field, but I think last year we are seeing a lot of stable diffusion going into full effect. And I saw a lot of, I think people working in the more of a design industry, I think feeling very, I think, depressed too, because of what they can do what humans cannot do. I think that was also kind of similar when the AlphaGo was beating all the human players. So I think it's not, we cannot say that I think AI right now is not really regulated at all. But then it is possible that AI might get regulated in future, I feel, because of many reasons. I think there are a lot of side effects coming too. So if that regulation happens, then maybe it's not about how far we can get in terms of technology. It's more of a, yeah, I don't know. It's like how far we can get as we are not having too much bad side effects. Yeah, so I think it's something that I'm wondering too. So one is that how far can we get technically, but then if we can get really far, then do we want to get there? Yeah, that's yeah, question that I have these days.
Yeah, that's a very philosophical question, and it also speaks to our career too, right? So are we
Exactly.
gonna...
Yeah, I think so too. Yeah, I don't think there's anyone who's free from being replaced, to be honest. I mean, I'm not saying it's 100% replacement, but then it's more of a, well, you needed 10 people for that, but then now you only need 1 or 2 people. Then the other 8 or 9 people are being, yeah, replaced, kind of. So yeah.
Yeah. So what do you think? What do you tell your students in what's going to happen in 10 years?
Yeah, I think it's really hard to predict given how fast things has been changing in the past 5 years. I think I would like to be open. Like, I think it's possible that we will see AGI in our lifetime. So it's also possible that NLP will be solved in 10 years. But I would probably, I think I do echo what Minji and James mentioned. So even if we create something that's as capable as the best expert in every domain, it doesn't necessarily mean that it will be a good collaborator to humans, or it will be beneficial to society. It could be very capable, but it's not necessarily safe or beneficial. So I think going forward, that could be a challenge. So assuming the capability will keep growing, how do we make sure that while they're becoming more powerful, they're also beneficial to humans? So specifically, I think for research, maybe HCI, AI safety, and or even AI policy and governance could be more important going forward.
Yeah, I think that is loosely tied to my last question, which is that, so this research collaboration center that we have between NYU and KAIST, the center's name is Inclusive AI. And the motivation for that is that, as we saw in the talks today, most of NLP research is on English. We ourselves do a lot of research on English. And James and I have this little project on how ChatGPT can do well in other languages, especially low resource languages. But so moving forward, if AI were to progress at the rate that it is now, and when we're thinking about NLP, it's an especially important question, because people in the world do not speak English. Not everybody does. And, English is now so far ahead of everybody, all the other languages. So first of all, how can we do collaboration between NYU and KAIST and perhaps other universities around the world to make sure that we are covering more languages? And also, does it mean just collecting more data? Is that going to solve this multilingual problem? Or is there something more inherent, more inherent and more challenging? And do you have some specific ideas of how we can collaborate to make NLP more inclusive? Do you have ideas? Do you want to start?
Yeah, so first question comes to my mind is, what's the current state, right? So we know that ChatGPT can perform in many different languages, but is the performance similar? And also, if I now do RHF or instruction tuning in one language, what's the effect on the other different languages? I think it's both important for understanding the generalization of these models, and also for making sure these models are inclusive. And I think we also discussed last time we visited, like, are the model given different answers in that are grounded in a specific cultural context? So I feel maybe the first step is to just better understand how the model is handling different languages right now, and are there biases or unfairness for the non-English languages.
Yeah. You're right. You're right. I mean, I don't think we have a good understanding of how these models are doing for all, like, thousands of languages that we have. And so even something like Korean, sometimes it does well, sometimes it doesn't, but there's no, like, systematic way to measure what the difference among these world languages. And I think, so going to Minjoon, I'm going to ask him now, in terms of knowledge too, right? So you were talking about how knowledge changes over time, but knowledge also changes according to geography as well, right? What we know in Korea is different from what we know, what they know, what people know in the US or in Thailand or whoever. And so including that question, what do you think about this whole, this question that I asked?
Yeah, I think, as you said, although we were trying to create a benchmark, I think, as you said, it's far from perfect or far from complete, because I think that there's much more to subtle knowledge than very objective knowledge. I think like these things like who was born and where, it's like something that no one will dispute. But then, as you said, there are many more things that are disputable. And right now, for instance, like AI, ChatGPT, for instance, just like OpenAI just prevented from talking about anything that's controversial. But I think that's because they cannot control it, right? Because it doesn't mean that we cannot talk about that. It's more of it's controversial that they don't want to touch it. And I think that's definitely something that, we have to work more on, because we definitely want to talk about it. And of course, it's not clear. If you just stop, I think what I'm saying is that it's not just good to say language models should not talk about anything controversial, because that's, I think, that's first step. That's a good step, because they can prevent bad things, but then it doesn't actually mean that it's something that we should be satisfied with, I think. So then we'll probably move towards more of okay, we're gonna talk about now controversial things, but in a more safe way. Then in that case, I think what you said, this kind of research becomes much more important, being inclusive and also, so, and I think then those things are very hard to measure. So there is a lot of, especially benchmark wise, I think. So I think that's really important too.
Yeah. That's a good point. I didn't think about so having NLP models, language models that can talk about controversial things in a safe way. That's a good research topic. I don't know how to do that though. I mean, how would you do that? And people don't even know how to talk about controversial things in a safe way.
That's true too. And also it's really hard to define that too, I think. But I think, if it's something controversial, then I think it's something that it's still not solved. So it's not, I think, the best way to just not talk about it. So
yeah. Well, so there is work on argumentation mining, and people talk about different viewpoints. I forget, there's a data set on different viewpoints on topics such as abortion or capital punishment, and then people take sides. And so, but I guess I should look at that literature again. It's interesting. And James, what do you think?
So we have language models which are trained by certain people, designed by certain people. They're using data written by other people. And then you have a third set of users who are making queries to these language models as well. And each of those people have different intentions when they write the data, which the language model is trained on. The researchers have different intentions when they make the model. And then the users of the model also have different intentions, different value systems. And what we don't know yet is how the value systems of each of those are affecting the end users of the language model, and whether those value systems are compatible. So I think the advantage of having wide international collaboration is that we can start questioning some of those value systems from the cultures we know. And hopefully that might give us a framework to study the bias and ethics of those large language models and the values they encode in a wider set of cultures in the future as well.
Yeah, really good point. And I'm sure we can have another 2-hour-long discussion about the values encoded in language models, but we'll perhaps do another one of these. So we went a little bit over time, but I want to give each of the panelists just one last thing that they want to say to wrap up this meeting, and then we'll personally will reach out and get this collaboration going. So James?
Can I just repeat what I said? Like, there's a lot of challenges in maths, and like it may seem like if you go on Gizmodo or News or something, you see LLMs appear to be solved, but they aren't. It's just we've got a very complex system which acts like a black box to us, and we're just kind of it reminds me of Harry Potter when you have the tea leaves and you kind of get a prediction from the tea leaves. We're just finding different ways to stir the tea leaves, and in the long run, that's not going to be a sustainable way to understand these black box systems. And as AI gets more and more complex, there's going to be more and more interesting questions which come, and we need to build the frameworks to study those in the future.
Great, thank you. Minjoon?
Yeah, I think one last comment is I think things are changing so fast these days that I think it's really important to take care of our mental health. Yeah, if you're a researcher, but not just researcher, but also I think everyone. So
Yeah.
yeah.
Wow, that's a good point. Yeah, thank you for that. And I need my mental health checked today and every day too.
Yeah.
All right, and
Yeah, I think it's really good that we're talking about these problems, and there are lots of uncertainties and challenges that we want to solve going forward. But the first step is to sit down and talk about the problems like what we just did. So yeah, I think it's a great venue and great opportunity to get things going, and hopefully we'll figure out the directions.
yeah. Okay, thank you. And thank you, especially because I know it's pretty late. It's like 10 p.m. or past 10 p.m. Where you are. I hope everybody had a good time, and we will be releasing the recording. If you want something taken out of it, please do let me know. Otherwise, we'll be forever on YouTube. And thanks everyone for joining and your questions. And I will see you later. Bye-bye.
Bye. Thank you.
Bye.